Alright, grade 12s, welcome back. We're going to take a look today at section 1.2 at reflections and stretches. We're going to focus on developing an understanding of reflections and their related equations, and on understanding the effects of stretches on equations. So a reflection creates a mirror image in a line called the line of reflection. They do not change the shape of the graph. However, unlike translations, reflections may change the orientation of the graph. When the output is multiplied by -1, the result is y equals negative f of x, a reflection in the x-axis. When the input is multiplied by -1, the result is y equals f of negative x, a reflection in the y-axis. So let's take a look at example 1. First, we're going to be given f of x, that's the graph down here in blue, and then we're going to graph y equals negative f of x and y equals f of negative x. So negative f of x is a reflection in the x-axis. We're taking the output and multiplying it by -1. That means whatever the y-coordinate is, we're going to change the sign of that. It's going to be a reflection in the x-axis, as you'll see. So I'm going to take a look at that point A there. It has a coordinate of -3, and we're going to change that to +3. Same with B. C is on the x-axis, so it's not going to change. D was at 4, so it's going to come down to -4. And E was at -4, so it's going to go up to +4. Notice I'm marking all these points down as A prime, B prime, C prime, D prime, and E prime. For the second one, y equals f of negative x, we've built a little axis over on the side here. I'm redrawing the original function in blue. Points A, B, C, D up here, and E. And then because we're changing the sign of the input, we're changing the sign of the x-coordinate, then that's going to be a reflection in the y-axis. The x's are going to change sign. So A, which was at -4, is now going to go to +4. B, which was at -2, is now going to go to +2. Notice the x values aren't, or the y values aren't changing here, just the x's. D was at 3, now it's at -3. And E was at 5, so now it's at -5. Connecting the dots, and we're going to label this. This is our second image, so I'm going to do B double prime and C double prime, etc. So these are reflections in, the first one was a reflection in the x-axis, the second one was a reflection in the y-axis. So how are they related to the original? Well, y equals negative f of x is a reflection in the x-axis. Any point x comma y is going to be mapped to the point x comma negative y. Also note points on the x-axis, because it's being reflected in the x-axis, points that are on the x-axis are invariant. For y equals f of negative x, the red graph here, it's reflected in the y-axis. So points like x comma y are mapped to the point negative x comma y. It's just the x-coordinate that changes. The y-coordinate stays the same. In fact, points on the y-axis, in this case, are invariant. That's my line of reflection. So points on the y-axis are invariant. Now, we move on to stretches. Vertical and horizontal stretches. I'm also going to use the word compressions in there in certain cases. So stretches change the shape. Okay, they don't change the orientation, but they change the shape of the graph. In this case, when the output of a function is multiplied by a, then we get a vertical stretch by a factor of a. When the input is multiplied by b in this case, then we get a horizontal stretch, but by a factor of 1 over b, and that's important here. It's important to remember that. Careful. Also, if a and b are negative, then we also get reflections. We'll see that shortly. So let's take a look at example 2. In this one, we're given f of x, that's that w-shaped function, and we're going to transform it, describe the transformation, etc. So we've got g of x is equal to 2 f of x. That means we've got an a value is equal to 2, so we're going to have a vertical stretch by a factor of 2. So everything's going to get twice as high. Nothing's going to go any wider, it's only going to go higher. So that first point's at 4, it's going to get doubled to 8. This point of 3 is going to go to 6, 2 to 4, 1 to 2, 0 stays where it is. 2 goes to 4, this point over here, 4 goes to 8. So notice I'm just picking key points and I'm doubling their y-coordinate. Points on the x-axis don't change, they're invariant. So we can say that this function, if we describe the transformation, it's been a vertical stretch by a factor of 2. We can say that, what did we say here next? The x values are not affected, they don't change. It's only the y values that change. Points on the x-axis are invariant, and those would be negative 2, 0 and 2, 0. And we could talk about the domain and the range. So the domain in set notation are all the x values such that x is greater than or equal to negative 6 and less than or equal to 6, and x is an element of the set of real numbers. We could also put that in interval notation and show that it's all the values from negative 6 to 6, inclusive with those square brackets. The range in set notation is y such that, all the y's such that y is greater than or equal to 0 and less than or equal to 8, where y belongs to the set of real numbers. And in interval notation, we could say that the range is all the values of y from 0 to 8 inclusive. Okay, well, let's take a look at that second case here in purple. Let me just clear up the mess here. So in the second case, we have an a value equal to 1/2. Sorry about that. So our a value is equal to 1/2. That means we have a vertical stretch by 1/2, which really means we're going to compress it. It's going to be half as big, not twice as big. Okay, so half as high. So I just used those same points, and instead of going to 4, I went to 2. Instead of 2, I went to 1. So you'll notice the graph is being compressed vertically. Okay, so I call that a vertical stretch by 1/2. The same invariant points. Okay, all the points on the x-axis. This time the domain, we'll just do interval notation here, stays the same, negative 6 to 6, but the range is only from 0 to 2. In the third example, we're going to look at horizontal stretches and compressions. That's when we've got a b value multiplied. So in the first case, we're looking at f is equal to, or g of x is equal to f of 2x. This is a horizontal stretch by a factor of 1/2. Remember, it's 1 over b. And the second one here, b, is a stretch by 2, because we're going 1 over b. 1 over 1/2 is 2. So for a, it's a horizontal stretch by a factor of 1/2, or a compression really. It's being squashed horizontally. All the points are coming in towards the x-axis. And for b, we're looking at a horizontal expansion, a horizontal stretch. So all the points are going away from the x-axis. Okay. So we're looking at a series of useful points, convenient points for us, and we're on the original function, and we're stretching them out horizontally. Our invariant point this time, our single invariant point, was on the y-axis. The domain of the first function of a here in purple, our purple function, I think I'm changing that d to a purple one. So the domain of that function, in interval notation, just to save some time, goes from negative 2 to 2, and the range goes from 0 to 4. The domain for the second function, f of 1/2 x, it's been expanded horizontally, it's been stretched, so my domain now is from negative 8 to 8, and my range stays the same, from 0 to 4. All right, final example. Example 4, we're just asked to come up with the equation for these transformations. Now in the first case, this is a particular case where we've got an absolute value function, and there's two possibilities for this one. We could look at it as being a vertical stretch, or we could look at it as being a horizontal compression, a stretch by a factor of less than 1. In the first case, we'll look at the horizontal compression, because we're going from blue to red. And then the second case, we'll look at the vertical expansion as we go from blue to red. So first case, we've got a horizontal stretch by some factor. How do we figure out what that factor is? Well, if we look at a point on the original function and see how it maps to the new function, we can figure that out. Making this a little smaller here just so we can get more writing in and still see the graph. So on the blue graph, we've got a point, it's actually negative 6, 6, not negative 5, 5. So negative 6, 6, and that maps to negative 2, 6. If I look at another point, I've got negative 12, 12, and that maps to negative 4, 12. That means any point that I've got, x, y, is going to map to 1/3 of x, y. The y doesn't change, but the x value is 1/3 as big. That means that g of x is equal to f of 3x. Remember, the b value is the reciprocal of, I could also say g of x is equal to the absolute value of 3x in this case. The second case is the vertical stretch. Now this is a vertical expansion. I'm going from blue to red. If I pick a point like 4, 4, it maps to 12, 4. If I pick a point like, sorry, not 12, 4, 4, 12. If I pick a point like 2, 4, that shouldn't be 2, 4, that's 2, 2. If I pick a point like 2, 2, it maps to 2, 6. I think I'm clearing that up here. 2, 2 maps to 2, 6. That means any point x, y is going to map to x, 3y. So g of x is equal to 3 times the output, 3 times f of x, or in this case 3 times the absolute value of x. So there's our equations for the two possible equations for A, the two possible functions. In the second one, we don't have any stretches or compressions because the shapes are the same. All we have is a reflection across the x-axis. So again, if we look at convenient points in mapping, this allows us to figure out what that factor is, or how to write the reflection. You'll notice that 2, 2 becomes 2, negative 2, 4, 4 becomes 4, negative 4. That means x, y becomes x, negative y. And it's the output function that's being multiplied by negative 1. So g of x equals negative f of x, or g of x equals negative the absolute value of x. Finally, I want you to look at the key ideas at the end of this section, section 1.2, and really read through there and have an understanding of what happens for y equals negative f of x, for y equals f of negative x, y equals a times f of x, and y equals the f of bx. Make sure you're paying attention to invariant points. You're identifying those, and then take a look at the homework. Okay, we're going to work on these questions in class tomorrow, but it would be a great idea, especially to look at those essential questions, 1 to 6 and 8 to 10.